For lesson 9.6, we are looking at taking a function that we've been working on this chapter and not just getting now the area under that function, but if you were to take that function and rotate it 360 degrees around the x-axis, it would form a solid like the one that you're seeing here. So the line that we started out by graphing was this line right here. This is y equals 2x. And if we were to take this line and rotate it around the x-axis, like you're seeing here, 360 degrees, you can see that it forms a triangle. Most functions will form some kind of a solid that you're familiar with, like a cone. But in any case, we are now finding the volume of that solid that was formed when it was rotated 360 degrees. And there's a little background explanation that you're seeing right here. I'm not going to go too into depth on that. What you really need to know for this section is this formula right here. So we are still dealing with doing the integration process, a definite integral from a left bound to a right bound. So a little extra thrown into this formula because we're dealing with the volume of a solid is to square our function and multiply it times pi, and this pi will come in at the end. Just like any other constant, when you're doing an integral, you can pull out the constant and save it for the end. So I did attach another video to today's calendar, so you can take a look at that. He had some good drawings that might help give you a better visual on what's taking place for this, so I encourage you to look at that. It was a fairly short video. But let me go through a couple examples of what we are going to do. So if we take the function from up top, which was y equals x. Sorry, I think I said 2x earlier, but it's y equals x. So if our function right here is x, we're going to be doing x squared. That's the first step on this. We're then going to integrate our function. So you square it first. You scroll down. So we squared it first. We're then going to integrate it. We will then evaluate it from 0 to 4. We'll then bring in pi into our answer. So we squared our function first. If we integrate this, you add 1 to your exponent, it becomes a 3. We then divide by 3, and so we get this look here for the integral. So we're now going to evaluate that from 0 to 4. So if I plug in a 4 first, now one option that you do have is to factor out the 1/3 as well and save that for the end also, like you see here. You don't have to do it that way. Either way should get us the same answer that we see at the end. But at any rate, we're going to plug in the 4, we're going to plug in the 0 and subtract to evaluate from 0 to 4. And so we get this look here, and oftentimes we're going to be asked to leave our answer in exact terms, just like you see it here. So that's what we can do. If we did need to plug that into our calculator, we can get a decimal to 3 sig figs. It's just one of those things that you always check the directions on a test for. And you can see by the geometry of it, if we were to use a geometric formula, we could have come out with that same function. The only problem with the geometry formulas are the shapes that are created, the solids that are created, don't always fit a nice clean geometry formula like this one did. So we kind of need the integral process to do just about all of these. And take this one for example. If you were to take this curve, this is the y equals x squared curve that you see right here, and if we were going to rotate that around the x-axis, this would be similar, a little more similar to one that we saw in the video that I linked to the calendar, but at any rate, it creates kind of a funnel shape, not a clean cone or triangle shape, and so we have to, or pyramid shape I should say, and so we really need the integral process to do cases like this. So again, our process on this is to take our function of x squared, square it. So we're going to come out with x to the 4th. That's our first step. We're now going to integrate our function. So it becomes x to the 5th over 5. We can now evaluate that from 3 to 0. So there we are, plugging in the 3 and the 0. And then we make sure that you throw in pi. I do remember from previous tests, oftentimes students forget to put pi in there. So we save it for the end. And so I think because of that, a lot of students forget to include it in their answer. And it does cost you points. So don't forget to include pi in your answer on this. You do have this formula in your formula packet. So if you point it out to you real quick, but right here we have the volume formula right there. And so you can see it does include pi. So if you are looking at the formula packet during a test, that would be your reminder right there. So make sure that you take the time to do that. Anyway, so again, if you want to give one of these a try, this is a good time to stop and do that. But again, if you were to take a function like this, quick reminder, when you have something like the square root of x, let's put that into friendly terms. So right here I have 2x to the 1/2. So the first thing that we would do on this is to square the entire function. So that would become a 4. 1/2 times 2 just becomes 1. And so this is the function that we get after we square it. And now we would integrate the 4x. So you're going to get 4x squared over 2. And that's going to bring us down to this setup that you see here. Of course, the 1/2, the 2 that was on bottom, and the 4 can reduce. And so you get to this look. Now you would evaluate from 1 to 6, and then make sure you include pi in your answer. All right. And then there's just one more case. Not a whole lot different on this, other than when you have something like x squared plus 2. So if we have a binomial, if I'm going to do a binomial squared, remember what that means. You're doing x squared plus 2 times x squared plus 2. And so most students will see that as FOIL, and so you do need to distribute that out, right? Remember, you cannot just distribute an exponent. That's a common mistake made on these. You have to distribute these terms to each other, and so you got to multiply the binomial times itself. That brings you to here. But now you can integrate from this stage. For the second part of these notes, the difference that you're seeing on these is instead of seeing the area formed when you just rotate around the x-axis, this is now the volume between two shapes, or between two functions, as it's rotating around the x-axis. And so now it's kind of linking this volume process back to what we did when we did the area between two shapes in our last video. This is the form that you would really want to see for this. This is not in your formula packet, so this is one you need to know. But it's the same formula for volume, but it includes now the difference between the two functions. And so you can see that setup right here. One thing I want you to keep in mind on this as far as the order of operations is you got to square each function before you subtract. And so I'm going to take the function that's on top. You can see in the drawing right here, that's going to be the parabola, the x squared plus 3. So that's going to be my first function, and I'm going to square that. I'm then going to do my second function, which is the y equals 2. I'm going to square that, then I will subtract. And so that's kind of the order that you want to approach these in. One thing that we have to do for this, when we go to evaluate the integral, we need to know our left and right boundary. And so the way that we're going to get those numbers is by setting this function equal to this function and finding out those points of intersection. And so in this case, that was happening from -1 to +1. So here we go with the process. So we have the parabola squared. We have our line squared. This is the two shapes. So we're finding the space between them. And so after you square each function, so that was the first one squared, here's the second one squared. At this stage, if you notice right here, you have two options. I can deal with these completely separate and subtract at the very end, like what you're seeing on this process down here, or you have this option as well. And to tell you the truth, this is going to be the easier way to go. You don't want to do two different evaluation processes like this one is showing. It's way easier to just do it once. And so after you square each function, subtract, then go through the integral process from there. And so at this stage, after we squared each term, like you're seeing on these, right at this stage is where I would have subtracted. And so then I would have dealt with the integral process from there. They didn't take that process, but that's okay. Either way works. It's just which way is shorter, which way is less work. And so anyway, from this stage, they did the integral of both functions, evaluate each one from -1 to +1, and then subtract the two results that you're seeing right here to get the space between them on this one. If you want to give this one a try, give a pause to the video and give this last one a try here on your own. So again, Helps to know on these which one is on top and which one is on bottom. So either a sketch in the calculator or by hand would come in handy. But you can see based on the drawing that the 2x is on top. So that's the one that needs to go first. The x squared is below it. And so we are going to find that shaded area between them when it's being rotated around the x-axis. So here we go. When we go to set up the integral for this, one thing we're going to need to know is where do those two functions meet? And so if you set x squared equal to 2x, we can solve just like you're seeing on this for those 2 points of intersection. So those give us our left and right boundary for the integral. We're going to pull out the pi and save that guy for the end. So first things first is we need to square each function. So if we square the 2x, we're going to get 4x squared out of him. Square that guy, you got x to the 4th. And so right here, now you're seeing what I was talking about in the previous problem, where let's just do the evaluation process once. So let's just subtract these two first. And in this case, there are no terms to combine. If you would have done this in the previous problem, you would have been able to combine like terms. You would have done 9 minus 4, and you would have just had a 5 right here. But then you would have integrated from here, but you only have one function. Same idea on this. We're going to subtract, but there's no terms that are alike for us to combine. So we just keep them separated by the minus sign. But if we were to now integrate each function, so this one's going to become x to the 3rd over 3. This one becomes x to the 5th over 5. And so we get this look here for the integral. We can now just do one evaluation process from 0 to 2. So plug in a 2 and a 0 and subtract. And it's going to bring you down to this look here. And then we'll bring in pi at the end, and we have our volume.